Good morning, everybody. Good morning. Hopefully, you can all hear me okay. Everyone can hear me at the back, and people up there as well, which is good. Yeah, welcome. Good morning, everybody. Welcome to ABL's market briefing, February market briefing. Let me just get this to work. Yeah, I'm for those of you who don't know me, I'm Adam Jackson. I am Director of Engineering UK, also the head of ABL Yachts, and I'm also a surveyor and a naval architect as well. So hopefully I can understand some of this presentation today. Our briefing this morning is accredited by the Chartered Insurance Institute, and delegates can claim up to 1 CPD hour for your participation. We will therefore keep a record of those of you in the room today and those of you logging in online. If you hadn't done so already, please make sure you sign in with the team at the desk outside the briefing in order to be able to receive your follow-up email and CPD certification. Just a quick reminder today as well, we will be ending the webinar portion of the briefing after the technical presentation, and the marine casualty case reports moving forward will only be presented in person for those of you in the room. Of course, we're happy to discuss with anyone who would like more information on them post-briefing, and to look at how we can make that data available to you for those of you online if you're interested. So if so, please come and see me afterwards. So I'm delighted to introduce our technical presenters today. We have Andrew Hinshaw, Andy, a good friend of mine who is ABL's, one of our ABL yacht surveyors, also a marine surveyor. Andy will be presenting today on the topic of motor yachts and sailing yachts, their stability risks, and what can lead to a total loss. Andy joined us just last year. He's quite new to us still from his previous role as a senior surveyor and head of large yacht services at the Maritime Coast Guard Agency, which was my job 2 years ago. He brings over 25 years of experience in the industry and has worked extensively on super yachts of 50 to 70 meters as an engineer. It's great to have him here today sharing his expert insights into this interesting topic. He is a naval architect as well. And also to read this month's case reports today, we have Colm Stevenson. Colm is a civil engineer in the ABL Group's engineering development scheme, currently working for ABL for the maritime side. And we're equally pleased to have him return this month to present our marine casualty data. Please note as well that the usual caveats apply and the Chatham House rules as usual apply in here. And please also remember that the information contained in today's presentations and any opinions or comments expressed are those of the presenters, not necessarily of those of ABL. This is a really important reminder. We give this reminder each month, but it is extra important that you do this, please, for our CPD accreditation. But please, if you get the opportunity, your feedback is crucial to these market briefings, and we do act on all the feedback that we receive. This is why I'm presenting today and not Mark. No, I'm only joking. But it only takes a few minutes to it only takes a few minutes to complete, and please, we do urge you to do so if you have the time. We've looked closely at the data that we got back from last year, and that's helped us to put our agenda together for the year ahead. Also, your feedback is a critical component, as I said, to the CPD accreditation status, and allows us to continue to offer you this 1 CPD point per briefing. So we have a number of QR codes dotted around the place to use, and that will give you access to the feedback. We've got the QR code outside as well if you need to get it there on your way out. And also it will be sent through in the follow-up email as well, that QR code. So please use it. Before I begin today, we ask you to give just a few moments thought to seafaring men and women at sea today. Even though COVID-19 does seem to be increasingly in the rearview mirror. We know that seafarers are still working more hours than they should, and remaining on board longer than they should. There's still issues with crew changes around the world in various different places. And there's also, of course, a multitude of other factors going on in the world, which always usually have an impact adversely on the lives and conditions for seafarers. Many of us and our colleagues come from seafaring backgrounds, and so crew welfare is a cause that is very close to our hearts. And as such, we are signatory to the Neptune Declaration, which has undoubtedly played a part in many improvements to the lives of seafarers today. Please take a moment, if you can, to have a look into this and perhaps consider getting your own company to become a signatory of this important thing. So here are some of the learning objectives for today. So hopefully by the end of Andy's presentation, you will have gained an understanding of the history of motor and sailing yachts. You'll be able to describe fundamental stability concepts, quite simply, including the GZ curve. You'll also be able to identify the impact of damage stability on motor and sailing yachts. You should gain an insight into the forces affecting yacht stability and the potential total loss factors. And you'll be able to describe key strategies for mitigating stability risks. We will go over these again at the end of the presentation to make sure everybody's learned them, and there'll be a short test. Really. And so now I'd like to hand you over to today's presenters. So I'll hand you over to Andy.
All right, thank you. So yeah, it's not an easy topic to keep everyone interested, but just saw there was a few incidents in the news recently for accidents that are due to stability. So I thought this would be an interesting topic to give a bit of insight into that. I'm not going to refer to any of the accidents directly. I don't have any further insight over anyone else that's outside the news. Not party to any MEIB or anything like that. So hopefully it's a bit more interesting because it's in the news, and hopefully by the end you'll be able to read the news a bit better. So I'll split it up into two parts: GM problem and sailing yacht stability. And then, yeah, let's go straight into it. So yeah, the GM, I can feel people wincing already when I put this up, but I'm not going to go into big technical details or formulas or anything like that. I just want to talk about the GM, what can happen when it goes wrong. So I've got a couple of slides building up to that. So GM has two components, pretty simple, G and M. G is center of gravity. I think we all instinctively know what that is, distribution of weight. But the M is a bit harder to visualize. Certainly, I've done a naval architecture degree and I find it hard to visualize. So thought I'd have a go at trying to explain it in 5 minutes. So if you take the underwater bit of the hull, the buoyant bit, you run it through a computer, you do your calculations, you get a value M. It's an imaginary point. You get a value M. You get a different M for one boat than you will for another. And what I'd like to press home is the height of the M is how it's inertia to rolling. So how if you wanted to move the boat, if it was a very stiff boat, wide, and it was difficult to put into a roll, you'd need a long bar to get it rolling. If it was like a log, a Canadian log, you wouldn't need a very long bar. So it'd be very easy to start rolling. That's the height of that M is how the boat will behave in terms of its rolling. That's all you need to take from this bit. So I've got this nice picture of a fisherman. When we were in the MCA, we had to do tests on fishing boats. We had to put the fishing boat into a roll, and then we time how long it would take, and that would give an indication of stability. This is just like a visual, a way of visualizing it. If you had two boats, it's a good way to get someone from Northumberland to say boat as well. If you had two boats and you had to put them into a roll, the one that's behavior is easy to roll. You could tie the rope quite low down, get it into a roll. But in another type of boat, different hull form, you'd have to maybe climb up the mast, and that's what this guy's doing. He's had to tie it up high because he needs a bit more of a moment to get it into the roll. So that's what I'd like you to visualize. So these are the, moving on to the next bit. So you've got that vessel with the high GM, which is, it's got that high inertia to roll in. And then you've got a vessel with a lower GM. It's it'll go into a roll easily. Coming further down to 0 GM, it is on a knife's edge. I picture it like a cyclist at the red lights and his feet are trapped in the pedals. He's just about to fall over. That is not an ideal situation. And then furthermore, negative GM is an unstable situation. The boat will go into capsize. So if you can try and visualize these 4 states of GM. So you've got a high one, very stiff, low GM, we call it tender. 0 GM is on the wobble. A negative GM is unstable. So now we go into what could happen to GM. So this is a beautiful yacht that I've put up here, yet to be painted. So, and then for whatever reason, they flooded that middle section. So that what I talked about earlier, that underwater portion of the hull, is changed shape. So it's a different shape. You run it through the ChatGPT or whatever, and you get a different calculation of M because it's a different shape. And would you believe it? M goes down. So coming back to that slide, if it was flooded, M goes down. So you've gone from a high GM to a lower GM. And then I've got this really extreme example with some numbers. You've started with a 1 meter GM. Well, for whatever reason, you've flooded a compartment. You've reduced it by 1.1 meter, and then you've gone to that negative GM. It's become unstable and capsized. I just got that picture off the internet. I'm pretty sure that's capsized. So yeah, that's the idea of what can happen to GM if you got flooding. But what's more in the news, I believe, is certainly fishing boats are susceptible to this. There's some MEIB reports. So GM, 2 components. We've already talked about it. We've already talked about M and what can happen. If it's not flooded, what can happen is G can rise. So the way your loads are distributed, it's changing all the time. So when you're consuming fuel and water from your double bottom tanks, your center of gravity will go up. And then I've just threw a few examples in there, filling a jacuzzi on the top deck or swimming pool. I've put passengers in there because passengers are not so much of an impact on yachts because they're limited to 12, but sometimes they have anchorage parties when there's 50 people on board on the sun deck. Certainly domestic passenger vessels are more susceptible to that. Modifications, this is the big one. When fishing boats in particular, they add fishing gear, they take down, add a gantry crane, that can significantly increase the VCG of the boat. And then you just need to Google MEIB reports for fishing vessels that are lost because of a modification is being done, and then the process hasn't been followed afterwards to make sure suitable ballast hasn't been put in. Putting a large tender on the deck. So the yacht gets delivered with a nice rubber dinghy in, and the owner wants to put a bigger tender on deck, that can change it. I've put ballast in there. When you do all these calculations and you decide that there has to be 16 tons of ballast in the hull or the keel, sometimes it's laid out in lead ingots, so it's in a tank, and you need to remove them to do some steel work or painting, and it's all controlled with a class surveyor and drawings. But in a different environment, if it's not controlled, maybe all the ballast doesn't go back in. I've never heard of an example like that, but possible. That's why there's steps in place to prevent it. Re-engining, if you've got a ship with engines that have reached the end of their life and they change them, maybe the engines are lighter. So that would, all of these things could increase G, and that would reduce GM and possibly lead to a capsize. So you're probably thinking, why don't they just make the Meta Center a safety factor of 100, which is what I thought as well. So this is the problem with GM. A vessel with a really high GM is really trying to come back up to its upright position, and when it goes under very high acceleration loads when it's trying to right itself, and it can be a very uncomfortable boat to be on. I was talking to a ship manager in Riga a few weeks ago. They manage some container ships, and they were saying they actually have a maximum GM that the ships can operate in, because the container securing equipment can get damaged if the accelerations are so high. So it's, for passenger comfort, it's more desirable to have a low GM, and then it's a more comfortable boat at sea. So there's that challenge for the naval architect to make a comfortable boat and ensure that there's sufficient safety factors in there that they can suffer flooding, or the crew can rise the VCG. Interestingly, I was talking to a naval architect in Whitby a few years ago, and he looks after, there's a fishing boat shipyard there. And he was saying if the fishermen come in and say it's a lovely fishing boat at sea, he just panics because he knows it's not meeting any criteria. The fishermen love a nice long rolling boat. So yeah, that's the end of the GM really. That's it's been known about for many years, and it's managed through good seamanship, good management, superintendency, good education of crew, qualified crew. So yeah, that's the end of part one. Part two, sailing yacht stability. So thought it'd be interesting to look at why sailing yachts might capsize. Fortunately, I've had to put a GZ curve in, but don't worry. There's only one thing I'd like you to take from it, because I found this picture on Google. I thought it was quite interesting. You can build the model in a computer, and then you can roll the model through its heel angle, and you can see this one's been rolled all the way to 180 degrees. But what's important is the positive range of stability. So you can see this one's up to, what's that, 130, 135 degrees. So that's where the boat is still trying to right itself. It's still trying right to the end, right up until 135 degrees to come back upright. And it's that positive range of stability that we'll see in the next slides will keep coming up as a solution to these problems. That this it'll all become clear. But as long as you understand that when I'm talking to the positive range of stability, it's this area above the curve. And that means that the yacht is trying to come back upright. So back in 1990, I think it was, the MCA commissioned. They were doing some work on a new yacht code, and they commissioned Southampton University to do a study for or sailing yacht criteria, really. And then Southampton University took that remit. They did a lot of studying on accident reports. They did a lot of model testing, which I believe that's a wind tunnel, which I'd never seen before. We didn't have that at Newcastle. When they did wave tunnels, wind tunnels. They did lots of model testing, and they also put a lot of equipment on existing yachts. And then they did a lot of empirical. They gathered a lot of empirical data. They did a lot of testing, and then thankfully they've come out with this report, and they've come out with 4 findings of why sailing yachts typically capsize and are lost, which is the title of this PowerPoint, fortunately. So we're going to take each one very briefly in turn and see what the report came up with a solution to solve it. So number 1, cargo or ballast shift. I think this is quite intuitive. They had a lot of data on this. There's probably a lot of data in this building where historically, I'm thinking like the Cutty Sark, the sailing ships transferred cargo, and then they heeled over for whatever reason, the cargo shifted, and then it couldn't come back upright. So they identified that as a risk. They actually didn't change anything in the code for that because they said yachts don't carry cargo, and the structure of the keel is already addressed by a classification society. But the author left that in the report, and I think it's still relevant because now with these yachts, they have big tenders in the garage, which it may not be considered cargo, but if it's not strapped down, it could shift. They've got furniture and keels that could fail, drop keels, raising keels. So it's still a very relevant risk. So left it in there. And then finding number 2. So this is just plain and simple, yachts being capsized due to wind. Interestingly, none of this report is about the size of the rig or the sail. It's all about the shape of the hull. And what they found was if a yacht had a positive range of stability up to 90 degrees, which is what we looked at on the graph, on the photo, it will survive, or it has a very good chance of surviving. So that's been built into the code now. Sailing yachts must have a positive range of stability of 90 degrees, and that will give them the best chance of surviving a capsize due to wind. And the next one, very similar. This is a gust. So the yacht is sailing. Don't picture a yacht at anchor. Picture a yacht underway. It's sailing. And then as a gust or squall comes through, so they're already at 15 degrees going across the Atlantic for 3 weeks like that. And then a gust comes in and takes them over to a further angle. And that if that immerses a down flooding point, so on your deck, you've got lots of openings for pipes and ventilation and access. The report found that there was previous incidents, Marquess, Isaac H. Evans, Pride of Baltimore, Albatross, sank within minutes after the down flooding point was immersed. So they went quite in detail in this about the Wilson report and how they could try and prevent that from occurring. And I'm really paraphrasing here, but really down flooding points are already identified on commercial ships. You measure the height of the down flooding point, you put it on the model, and you can see on the model when it's immersed. What they did on this Wilson report, they identified that on a bulk carrier or oil tanker, you've got a bit of notice before you're heeled all the way over to your down flooding angle. It's not so susceptible to being knocked over to wind, so you've got a bit of time to go down and shut the door. They said it's less likely for that to be able to occur when it's a sailing yacht because it can get knocked over. So they identified critical down flooding points. They put a formula in the code. I think it's displacement divided by 1500. And if the area of any opening ticks that box, it feeds into a formula, and we don't need to know what it is, but that tells the captain if he's sailing along at 15 degrees, they can could be a female captain. They can be assured that a gust will not take them down to the down flooding point. So it gives the captain a maximum steady heel angle. So they know, gives them an operating profile in which they can work in to prevent these down flooding points from being immersed, leading to capsize. So when I used to do the stability approvals, we'd do the stability booklet, and at the end, you'd come out with an angle of 18 degrees, and then that would be in the stability booklet, and the captain would know they'd have to stay within that. They also produce these squall curves, which are not as prescriptive. They're a guidance to the captain, so they know that if there's 30, 45, 60 knot squalls expected, they can reduce their sail accordingly. They can pick it off and get their angle from there. So yeah, that was the findings to reduce the risk as much as possible of down flooding occurred from a gust or wind. And then the last finding is this wave being knocked over by a wave. And it obviously the size of the wave doesn't change, but the yacht, it's proportional to the size of the yacht. So smaller yachts are more susceptible. And it said there was a lot of fastnet race in 1979. There was lots of people lost during that incident there, and they used a lot of the data from that. And what they found was a positive range of stability of 90 degrees. Come back to that again, which is what we talked about at the start. Gives you the best chance of surviving a wave, being knocked over by a wave. But I'd only worked with yachts over 24 meters. It wasn't until I was preparing this that I realized under 24 meters, the advice is a much higher positive range. So you can see it on there. A yacht of 15 meters should have a positive range of 120 degrees to prevent it from being knocked over by a wave, which I had not noticed that before. So yeah, that's rattled through it really. That is why yachts can suffer total loss of stability. We've looked at the insufficient GM, how that can change through the life of a vessel, how if it can get flooded or the VCG can rise. We've looked at that cargo or ballast shift, how maybe a tender's not stropped down properly. A yacht can get knocked down with it could be a wave or wind and then not come back up right. We've looked at the wind-induced down flooding, giving them a max angle so they don't get knocked down to that critical down flooding point, and then the waves. And then just what I'd like to really add about that down flooding point is none of those down flooding points are these watertight shell openings that probably didn't exist in 1990 when this report was written, where it's an opening in the hull which they use to launch a tender or put a beach club down. they're assumed to be closed and watertight throughout. So you can imagine what would happen if they were open. So yeah, that's the end of my presentation. Got questions, hopefully? Great. Mm. Doesn't so I've got to repeat the question apparently for the online audience. So the question is, does a sailing yacht under tow, does it affect the height of the M? No, because the M is calculated from the underwater portion of the hull. But there is so it's called a heeling moment. So it's what's pushing the boat over. It could be a wave, could be a wind, and towing is another heeling moment that could be trying to pull the boat over. So there's special considerations for towing in that respect, but not in terms of M. Yeah. So I think if there's no openings, if it's just a complete structure, it will be very, yeah, it will go as far as the positive range of stability, but that will change if there's no openings or, yeah. Does that answer your question? Not sure if it does. Yeah. And these are theoretical. Real life is different. You know, you can model it as much as you want. It might not behave that way in the middle of the Bay of Biscay, but yeah. Yeah, actually, do you know down flooding points? And I've never seen. I was thinking of this when I was preparing it. We don't actually model. I've never modeled it. I've never seen it modeled. The down flooding points, you don't model like the water surging in and how that affects. It's just it truncates it. So you've got to have enough area under the curve where the down flooding point immerses. The computer just cuts it off there, so that you only get up to that point, so you don't get the rest. Hope that helps. Yeah. Yeah. That is, well, it's on a computer. That's a laboratory condition, flat water. Yeah. Sorry, the question was this GZ curve, which is that modeled in flat water conditions, or is that it? If there is a wave come, could that influence how the ship reacts in real life? And yeah, for sure, this GZ curve is, as I understand it, flat water, calm conditions. It's a particular trim. You do several different GZ curves for zero trim, positive trim, negative trim. Yeah. Do we take anything from? I'm not sure. I've only been on the on the compliance side for the MCA, where we did an independent check. So a yacht would be built, and then they would do the stability booklet and they would submit it to the flag, and then we would take that data. We would also build our own model. We do our own check, and we would check that all these findings were introduced into the code. So we are also doing our own check that what they've proposed is meeting the criteria. I've never been involved in the design stage where a naval architect would build a model, and they do for sure. They see how it behaves in a seaway and resistance and propulsion. But for this topic, that's not necessary. It can all be done with computer modeling to check that it meets the criteria. So yeah, yes, they do it. But in terms of this presentation, it's not necessary to build a physical scale model to carry out any tests. But they did. They actually did. Producing this report, that's what they did. So that's where they got a lot of the empirical data from to get the findings. How do I look at that?
This is from Chris Zamet. There are particular rules on the connection of the keel to the hull. Loss of keel, in fin keels especially, would lead to loss of stability.
Yeah, that is, I touched on that on finding one. So that is this cargo or ballast shift. So if a yacht is sailing along and it's got a bull keel with a big heavy lead weight at the bottom, I think we can all appreciate if that failed, then could be a tragic loss. I think Cheeky Rafiki is the one everyone knows about. So what they said, what the code said was, this is already addressed. So if a yacht is covered under the large yacht code, it's with a classification society, that structural strength, the assessment for it, the regular surveys of it is all part of that classification process. So there wasn't anything specifically written in for cargo or keels. It's just, if a vessel has a classification society, it's assumed that that's all part of it. I think that addresses that.
Any thoughts on what happened in the case of the Bayesian sinking in Sicily and how her stability allowed that to happen?
Yeah, I mean, I said at the start, I've got no knowledge other than everyone else of what we've read on the news about Bayesian. So I'm deliberately not going to speculate on it, but I think the way I've set the slides up is for people to draw their own opinions on what could happen, and then we just have to wait for the MAIB report. All right. Yeah. I think the significant part of that, I'm so glad someone asked me about it. The significant part of that is the flooding and the M being reduced. I'm not sure about the healing moment. You would lose some of your healing moment by flooding. So, but this is a historical, it goes back to the Titanic when they worked out that GM needed to be of an appropriate size, and then keep an appropriate factor in for damage. The reason I left it in was because we know that some yachts don't have damage. They don't have subdivision. I've been on yachts and looked all the way to the stern. So there's some size of yachts that could suffer total loss with a small bit of damage, but most, I'd say all commercial ships and most commercial yachts, or all commercial yachts, have damage stability. It's built into the calculation that in a compartment's flooded, you've still got a reserve of GM, and then you've still got sufficient area under the curve. But yeah, the reason I left it in was because I know some yachts don't have damage. Yeah, yeah, yeah. If it's, yeah, you're saying if it's split longitudinally. Yeah, yeah. So what they have, I didn't put it in here, but there's also a damage criteria, a bit like that GZ curve. So you can do that. You can do that in the damage condition, and you can see what the resultant angle is. So if it's only flooded on one side of a compartment, it can end up being like that, and you can lead to further down flooding. It's difficult to launch the life rafts. So there's actually a maximum angle that if flooded, it can only go to 7 degrees. If it goes to 8 degrees, they're going to have to put some more bulkheads in, do something. Again, that's only for vessels with damage. Yeah.
One more from Francisco Blasco. What are the stability requirements for a yacht with not more than 12 packs and not engaged commercially, only private?
Yeah, this is one of Adam's pet projects, that trying to bring pleasure yachts into compliance under a code. There's no requirements really. So the only requirements I'm familiar with is the commercial yachts, where if you're taking paid passengers, you're built under a code, and then I was the person doing that independent check of the stability. And every 5 years, we would also go and do an incline check. We would distribute weights around the ship, see how it responded, to make sure that VCG wasn't rising too much, which I talked about in earlier slides. I would confidently say there's a lot more protection and steps in place to protect a commercial yacht than a pleasure yacht. Would be my response to that. All right. So is Adam coming back up now, or do I go back to this? Someone will have to help me. I can only do stability, not. Yes.